All right, number 5. How long will it take a car to accelerate from 20 meters per second to 26 meters per second at a rate of 1.4 meters per second squared? How long will it take is time. So we're actually not trying to find the acceleration because they give it to us right here. And they give us two velocities. So basically, we know like our acceleration is 1.4 meters per second squared. The starting velocity is 20 meters per second. And the final is 26 meters per second. We're trying to find time. Okay, so basically, we need the formula that has A, V, and T in it, which would be your average acceleration formula, which is change in velocity over the change in time. Now, in this case, we know this. We know the acceleration. We have the two velocities. That's how we'll find the change is by subtracting them. Remember, delta means change. And we're trying to find time. So we would put it in a formula triangle, basically. And since this is division, whatever goes in top is in the top. And A would be here, T would be there. Okay, so we're trying to find time. So it's the velocity, technically change in velocity, because we have the velocity changing. That's what acceleration is, a change in velocity. So change in velocity over acceleration. So to find the change in velocity, you want to do the final, take away the start. I should put units, so they like to see units everywhere in the MCAS. And then our acceleration goes on the bottom. It's on the bottom of the triangle. All right. So basically, when you subtract, you end up with 6 divided by 1.4. So 6 meters per second over 1.4 meters per second squared. And that should get you a number that's like 4.2857. So basically, they round that to 4.3. And that's how they get that. Okay? So you had to rearrange the formula for acceleration to solve for time. The tricky part is to remember to subtract to find how much the velocity changed. Then you divide that by the acceleration to get your time. Okay, so pretty simple though, using your formula triangle. We've done that before. All right. MCAS loves graphs. They love these graphs. It'll either be velocity or a position graph. This one's a velocity graph. Always pay attention to what's here on the y-axis. Time's always on the x. So we could see the velocity, since this is a nice flat line, the velocity is not changing. So we have constant velocity. And then we see the velocity decelerate down till it gets to 0. So it must be stopped right here. It has 0 velocity, so it's stopped. So what matches that? A soccer ball at rest and then kicked? No, because at rest it would have to start at 0, and then when it gets kicked, we'd see it accelerate, so it can't be that. A ball thrown up in return. Okay, so if we throw it up, we would expect it to slow down as it goes higher because gravity's pulling it down. So you expect the speed to kind of slow down, and as it falls, the speed would pick up again. The velocity would pick up because gravity would make it accelerate. So you'd kind of see the graph start to curve upward. So no. A person running at constant speed decides to run faster. Okay, well, we got the constant speed right, but running faster, the graph would have to go up. Speed or velocity would go up. The velocity would increase. So no way. So constant speed and then applies brakes and comes to stop. Oh, yeah. So we have constant speed. Brakes means decelerating, speed going down or velocity going down. I don't know why the MCAS uses speed and velocity interchangeably like that. It's kind of confusing for students. It's confusing for me, to be honest, because you shouldn't do that. But they're MCAS. They can do whatever they want, I guess. Anyways, so decelerates and then comes to a stop right there. We have 0 velocity. And yeah, that's it. So there you go. That's it. I mean, basically, notes what we got. Flat lines, constant, right? And decelerations when the line goes down. And when it's at the 0, that's stopped. I mean, the graph itself kind of, you just got to understand the graph. But there you have it, folks. There you have it. So, bam.